Good morning, and great to be here and with all of you, but also I'm very excited to introduce our first panel speaker, who is Professor Nicolò Cesa-Bianchi. Even though he's a Professore Ordinario at the University of Milano, he's anything but ordinary. He's actually extraordinary. And Nicolo has received a lot of actually awards. It's sometimes tough to introduce people like Nicolo because you have to memorize so many awards. So I'm just going to say a few of them. He has the Google IBM Faculty Award as well as the Criterio Family Award, and his research is in design and analysis of machine learning algorithms. And he has chaired actually really almost all the important conferences in machine learning except UAI, so we have to make you chair UAI. So all the way from NeurIPS, Fold, Alt, and so on. And Nicolo's work is not only influential in terms of papers he has written, but also in terms of the book he has written. So if you have not seen the book yet, you're really missing on it. So it's called Prediction Learning and Games. And it's one of the best, I would say, papers or books, manuscripts to actually use if you want to learn about bandits and even further. So I would say it's actually learning to do predictions, especially if you're doing it basically from this so-called individual sequences instead of the typical, like I would say, expectation setting. So without too much wasting your time, I'm sure everybody's here for Nicolo, not for my introduction. I'd like to ask Nicolo to give his talk. And he's a very good speaker. So thank you, Nicolo.
Can I get a picture and do I have to order? There's a mic over there, right?
So you can also use this one, Nicolo.
Yeah, but I can use this mic.
Okay, yeah.
All right. Thank you so much for the wonderful introduction, and thank you for being here. Okay, so there's two kinds of invited talks, and like invited talks given by insiders that are regular participants in the conference, and they sort of expound some core theme of the conference itself, and maybe invited talks given by outsiders that are maybe don't come to the conference regularly, and we bring some different theme that maybe could be of interest for the people here. So I think I'm going to the second time of invited speakers, and so we talk about something that is not probably a core theme of this conference, but yeah, this is the idea of bringing something new, and maybe raise your interest. Okay, so this is about co-connecting learning algorithms, and yeah, this is sort of a series of papers that started like a dozen of years ago, because I got interested in this topic. And these are some of the collaborators that were on these papers, and I won't cover like those are papers. I will cover pretty much a few of them sort of follow a logical development of the topic. So yeah, motivated learning is of course something very fascinating that it's very easy to get interested in, at least my case. And yeah, there's many. I mean, I'm taking a very broad approach to motivated learning. So I will, for me, like multi-robot systems, mobile sensor networks, or even distributed learning systems are instances of motivated learning. Of course, I will treat because I do theory, so I will treat the topic at a quite abstract level. So this is more like some motivational application, but I want really dive into any of them. So the idea is that we have several agents. They are learning agents. They may compete for some, maybe shared resources, or may cooperate to achieve some common or some related goals. And I will, in this talk, I will focus more on the cooperation side. And but clearly there's a continuum, right? There's a spectrum between competition and cooperation, depending on whether your goals are very much aligned or kind of orthogonal or zero sum. And another aspect is whether, you know, how do agents interact with each other? Can they talk to everybody? Can they broadcast a message, or can they only talk to a subset of the other agents? And maybe this subset is determined by some conditions like, you know, proximity. Think of a bunch of, you know, mobile sensors to do some recognition. Or maybe there are some, you know, energetic considerations, so they cannot really engage too much in talking to the others because their battery life can go run out. Okay, so let me now, once you know, I started working on this multi-agent learning, so I was looking at a certain in a certain direction because that was a kind of a natural direction for me. But then I sort of discovered that there are several dimensions and several axes along which should be research and investigation can be developed. So we can, okay, let's start. So there's a single agent learning, and the main idea, I mean, the way I view the single agent learning problem is how fast can an agent learn as a function of information received from the environment. So I want to optimally extract information from the environment in order to learn my task as fast as possible. Okay, you know, as efficiently as possible given information provided by the environment. So this is, I think, a fairly general definition of learning, and many of us can agree with this, although maybe not everybody. So now, if you move to the multi-agent learning world, you're adding a dimension, of course, and it means that you're not only learning from the environment, but you're potentially also learning from the other agents. So now you are integrating two sources of information, and you would like, you know, to get a better benefit by this integration, by this combination. So, you know, one of the things on the top will be, okay, under what conditions and to what extent I can actually learn faster if I also getting some help from my friends, from my friendly agents. Okay, right. So in our view, we will take a very some, you know, making things a little bit more concrete as I move on. So we will be looking at agents that sit at the nodes of a static communication graph. Okay, this is okay. It's not a mobile network; it's a static network. But of course, this assumption can be generalized very easily. And it has been done in several papers, so I won't mention that in the talk. So the idea then, okay, so now are actually agents learning the same task, and in which case I would I would talk about multi-agent single task learning, or do agents learn different tasks, but perhaps these tasks are somehow related, so there's some meaning in exchanging information, because maybe, you know, we're not exactly doing the same thing, but of course, you know, there's some relatedness that makes it, you know, useful to talk to each other. And in this case, I will talk about multi-agent multitask. And then another thing is whether all agents always participate in the learning process, or they may abstain or withdraw or be quiet for some time. Okay, this is a temporal dimension. So that is the learning synchronous or asynchronous? Okay, so we will be looking at a little bit of at these questions. Okay, this will drop me if you have any questions. Right. Oh, there's more. There's more. The thing is, yeah, maybe the agents don't have the total knowledge. They don't even know it. It's not okay. They have to learn a task, but maybe they don't have a full view of the task that they have to learn. I will be more precise in a little while. And then the other thing is that agents receive full or partial feedback from the environment. So in the first case, I will talk about distributed optimization, which is a sort of independent research team has to do more with federated learning, but I wanted to do it as part of this motivation setting. And the other case is motivation bandits. But I won't talk about motivation bandits because essentially there's going to be enough enough topic, enough material to cover without bringing in the bandit dimension. Okay, cool. So now, right? Yeah, if you know what I've done in the past, it's not really surprising. I will be studying these things through the lenses of online learning because this is what I know and like, and this is kind of a framework that makes it very natural to study these trade-offs between information, feedback information, and learning rates. Okay, so I want to understand how much this feedback information I receive from the environment together agents will drive the mind learning rates in an online learning framework. Okay, so the main idea is that we will look at basically three kinds of results in the multi-agent single task setting. So remember, multi-agent single task, they all cooperate to learn a single task, and we will look at the case in which one agent is active at every step. So now it's a sequential learning problem, so time goes in steps. And you will see that the performance scales with the independent set of the communication graph. So this is a graph theoretic notion that we will quickly introduce in a little while. If we now move to the multitask case and we still stick to the model, the asynchronous model in which one agent is active at every step, then we will see the performance will depend on the interaction between the local variance of the tasks that each agent is learning and the graph structure, which is not really surprising, of course, but we would like to see how this kind of interaction plays out in the analysis, of course. And the third is a distributed optimization when the agents don't get to fully see, their tasks in the online learning setting. And but in that case, we will consider all agents are always participated, so a completely synchronous setting. And we will see that in that case, the performance scales with the inverse spectral graph of the communication graphs. Which is, it's a kind of a orthogonal graph theoretic measure with respect to independence set. Actually, it's an independence number, not independence set, of course. We scale with the independence number of the communication graph. Okay, which is the size of the largest independence set. Okay. So, and we will, try to understand a little bit why this kind of graph theoretic quantities pop up in the analysis, depending on the kind of assumption we're going to make. At the end of the day, it's not so exotic. It's kind of natural that these things appear. Okay, so let's move on. Online learning is one of the paradigms, one of the frameworks in which you study machine learning, and it deals with data streams. And these data streams are nowadays kind of ubiquitous in many applications. And the online algorithms operate on these streams by incrementally adjusting their models, so there's no training in best phase. And we make in online learning, we like to make no assumptions on the way that these streams of data are generated. So everything will be absolutely deterministic, and there's going to be some unknown deterministic source that is generating the data stream. Okay. So let's see. Now let's start with defining this protocol. So we have agents. The agents are sitting at the nodes of the communication graph. And we have a decision space or monospace, which some X, you can think of a subset of the dimension of the Euclidean space, and time goes in steps. And at every time step, some agent, one agent is active at the time, so some agent is woken up and is requested to make a prediction. That guy, the yellow guy over there, And he will predict using its current local model. The pointer is not working, but it's the XT of BT. And we will incur some loss, which is the LTXT of BT. For instance, it's a square loss, if you like. Maybe there's some data point ZT and some label YT which are revealed afterwards. Okay, so the agent is unhappy because it's getting some loss, but then it's also getting some feedback. So typically we will think of first order algorithms receiving loss gradients as feedback. Loss gradients evaluated at their prediction. And at this point, using the feedback information, the agent may update the model and then share the feedback with the other agents. So the other agents are not active, they're not participating in the prediction, but they get a free update. So they get a free update, they can make an update without paying any loss. Okay. So of course, in this model, you say, okay, should I update with the gradient of the loss of this guy? Is this really something meaningful to do or not? Well, it depends on whether we think that all the, we are in a completely comparative setting, or we may be in a multitask setting. So the two things will be a little bit different. Okay, so we now define how we measure performance in this setting. So we assume we have now we can consider these loss functions, like a square loss. We can view them as a sequence of convex loss functions, as it is customary in nonlinear analysis. So we're going to receive the sequence of loss functions, and we have a sequence of agents of activations. And this defines a best local model for the stream of losses after T steps. So the best global model doesn't depend on the sequence of agent activations. It just only just depends on the sequence of losses, and it's just the best model minimizing the cumulative loss over that sequence. All right, and then you can define in the single task setting. You can define the regret as the difference between the cumulative loss of the agents that were activated in the sequence given by the sequence of agent activations. Okay, that cumulative loss minus the cumulative loss of the globally best decision for that stream of loss. Okay, this is the usual sequence of regret. And we are just now saying that, okay, now we are not measuring regret at the same agent, but we're measuring regret along the sequence of agents that get activated in the setting. Okay, cool. So now agents are activated, they have to make a prediction, they face some loss, and then they spread information around. And so, okay, so what happens here? Okay, so we will assume that losses are bounded, therefore the regret can only grow, even if we play with random, the regret can only grow linearly with time. So now, okay, let's pause for a while. Okay, let's assume there's only one agent. Okay, so how can we control the regret with a single agent? Well, there's a bunch of algorithms like nonlinear descent, followed the regularized leader, and then we give you a regret which is bounded by the square loss of the number of 10 steps. So the regret grows sublinearly with time, especially in particular with square loss. There are some constants there which I'm omitting, which will depend on the diameter of the decision space and on the Lipschitz constant of the loss. Okay, so now this algorithm will all use the loss gradient to update the models, and this rate is not improvable in general. So for any online learning, so not even in a single agent case, I can do any better than that. So there are lower bounds that hold for any online learning algorithm. Okay, so that's our benchmark for single agent learning. So now we bring it to a more general setting. So in the multi-agent setting, so let me make a few comments. We will assume that there's no central authority, so we will look at decentralized learning models, and we will assume that we will assume a simple like a very simple implementation. We just deploy the same learning algorithm with the same implementation, with the same initialization over all the nodes. Okay, so there's no, so in particular, agents won't be aware of the communication graph, or their position, or the topology of the communication graph, because they're all initialized in the same way. Okay, so it's a pretty strong assumption, but makes everything very simple from an algorithmic viewpoint. And we will also assume that agents can only exchange messages with their neighbors in the graph. Okay, so that's the only way agents can talk. Otherwise, why do they have a communication graph? All right. So yeah, so it's kind of very easy to see that if agents, all the agents run some standard off-the-shelf online learning algorithm like non-linear descent, and can talk to all the agents. So the communication graph is a key. Yeah? Then every agent will have the same state. So the states of all the agents will be evolving just in the same way, because information is completely shared, information. And then you can just get just the same single agent bound, because there is a single agent, because there is a single state for all the agents. Okay, so that's pretty trivial, but it's important. So how now? Okay? We take the click and we remove all the edges. So we are now isolating the agents. And let's say that T sub B is the number of times some agents is active. But now this is a very simple calculation. So now, how much each agent is running a distance of OGD. So the regret of each agent is the square root of the number of times that agent was active. And in order to compute the single task regret, we are summing up all these regrets over all the agents. And by just using Jensen's inequality, we realize that essentially we are gonna, the regret in the no communication case is gonna scale with the square root of the number of agents. Okay, this is a very simple calculation, but it's telling you that essentially, if you ignore communication, this is the worst case price you're gonna pay. The square root of the number of agents. That's how badly you are regretting scale, because we are not talking to your friends. All right. So now let's see, if you give me some communication graph with some edges, how much communication can happen here? So the idea, so let's look at the lower bound to start with. So let's assume we have again a single task. So all agents are learning the same task, and only the red agents get activated. The white agents are never active. They never participate in the problem. They never make a prediction. So the red agents form an independent set on the graph. So they're not no pair of red agent is adjacent. So but agents, they only talk to their neighbors, but their neighbors are never active. It means that essentially, even though we are in a communication graph, the red agents work in isolation. They work as they were in a graph with no edges, of course, because they will share information with the neighbors, but the neighbors are never active, so they cannot act upon that information. So the red agents will learn independently, and now we can prove a lower bound that says this essentially that what they will pay. The lower bound is basically the counterpart of the upper bound we saw before. So now the effective number of agents is the number of the red agents, which is exactly the independence number of the communication graph, and that is the regretted number of pay. Okay, so we can actually invert Jensen's inequality by activating all the red agents an equal number of times. So now that's the kind of lower bound we are shooting at. And okay, we now assume that agents are activated at random according to some unknown distribution. So we give ourselves a little bit of some randomness assumptions, but we see that this randomness assumption is kind of important. So we are looking at stochastic activation. We're still in the single task world, and we have a specific communication graph which is unknown to the agents. Each agent will run OGD with no specific initialization. And the neighbors of active agents will update their models using the shared loss gradients, just like in the way I showed you before. So what we can prove here is that the expected regret, where the expectation is with respect to the this stochastic activation of the agents is exactly upper bounded up to constants by the square root of the independence number of the graph times the square root of the rise. So we are actually matching the lower bound up to constants, and we call the agents that don't know the topology of the networks. In particular, they don't have to compute alpha. Computing alpha is actually hard, okay, in general, but they don't need to compute it. They're completely oblivious to the alpha. They just need to know what are their neighbors. So when the network is eclipsed, we recover the single edge bound because the independence number of the edge is 1. And when the network has no edges, we recover the no-edge bound because the independence number of an edgeless graph is exactly the number of nodes of the graph. So we are sort of a kite across all the spectrum. Okay, so that's nice. So yeah, so now we can see, okay, well, what happens if we just drop this assumption of stochastic activation? Why agents should be active stochastically? Well, it turns out that we can engineer a graph like a star in which the center of the star who talks to everybody will receive a sequence of losses which is misleading with respect to the actual best decision. So the center of the star has a bias review with respect to the actual best common decision, but it's spreading the information to all the neighbors. So, and we using the assumptions on the way the agents are initialized and talk to each other, we can prove a lower bound, a linear lower bound. Essentially, if you have arbitrary activations and if you engineer the adversary engineers the sequence of agent activations and the sequence of losses in a certain way, you can prove that algorithms like RGB will suffer a linear lower bound. So there's no learning possible. That's even worse than not communicating. So in this case, communication occurs even if all the agents are measured with respect to the same common best decision, which is X star T, which is the best decision for the entire sequence of nodes. Okay, so yeah, so we do need stochastic activations in this multi-agent 0+ setting here. Otherwise, we may run in this kind of lower bounds unless we make our model a lot more complicated. So if we assume that each agent can be initialized differently and has knowledge of the graph, then this kind of lower bounds can be overcome. Okay? Cool. Yeah. The lower bounds holds for any element, but only for that kind of yes. And only under those assumptions on the algorithms. Again, so the algorithms have to be oblivious to the network. Because otherwise they can simply avoid updating the design with the center. Yeah. Any more questions? Stop more often asking questions. Okay, so let's move to the multitask. So far we look at the case in which all agents cooperated to solve the same star. But now we assume that things might be different. So this is the single task regret which we saw before. So we were comparing the cumulative loss of the agents' predictions according to their activation with the loss of the best global model for the entire sequence of losses. Okay, so now let's assume, so all agents are learning on the same stream of losses, and the comparator doesn't depend on the activation sequence. So, the best global model doesn't depend on the sequence of activation. But now let's look at the following version of the S. So let's move the infimum over the models inside the sum over the agents. So now we are looking at for each agent D, we are looking at the best model over the sequence of losses that the agent is observing on the subset of the time steps where the agent is active. Okay, so now each agent will have a personalized sequence. We look at the personalized sequence of losses, and it is actually going to be scored with respect to the best achievement for that subsequence of the loss sequence. Okay, the subsequence where VT is equal to V, so that a specific agent is active. Okay, so now these best local models may be different from each other because they depend on the way the loss sequence is partitioned among agents, and this is determined by the sequence of agent activation. Very well. So what happens? So now agents learn on the local streams defined by their activation sequence, and so now we will now look at a slightly different interactions between the agents. So this model is a bit harder because we are now looking at a hardware comparator in which agents have to learn locally and cannot learn the same global objective. And so we will adopt a model, a two-round model, in which, same as before, an agent is requested a prediction, but now, first of all, the agent will pool the local models of the neighboring agents, will combine them to form a prediction, will incur some loss, we'll observe the loss gradient, and then we will share the gradients. So we now afford the agents to pull in the neighboring agents model before computing the local prediction. And this is slightly more complicated setting is justified by the fact that we have a hardware goal to satisfy. So is this model clear? Okay, yes.
It's not clear why the other has information will happen in my time.
Why the others? Sorry.
The other agent's information will help. It might have different.
Yeah, absolutely. It's not, on the other hand, you can simply ignore it. Yeah, so right. So it's not clear. So let's see under what condition this becomes useful. That's the idea. There must be some condition, of course. Yeah, think of if the tasks are very much different, that's going to be hard. If the tasks are the same, oh, that's great. So there's going to be some threshold. So we want to determine exactly the threshold after which it becomes harmful to share information. Okay. And it turns out that things are actually nice, otherwise I wouldn't be showing them. Yeah, so I want to only show nice things to do. Right, so in the single task, let's recall what we saw before. So before we had this square root of alpha, square root of t, and we had the stochastic activations. So now what happens now? So first, let's look at the case in which we have a team. Okay, let's multitask, but we have a team. Everybody can talk to everybody. So there are no communication constraints. And in this model, we can actually afford the deterministic activations, and there is no contradiction with the lower bounds. So the kind of bound that we can prove in this setting is the one that you see here. So the alpha, which was the independence number in the single task case, becomes that thing over there, the red thing over there in the multitask case. So what is sigma? Sigma is the variance of the single model, which is the kind of thing we would expect, right? So every agent has a model. A model is a point in the d-dimensional model space. So that's about for 8 agents, that's their bunch of models. They may be very clustered or kind of spread out in the model space. The model space is bounded because the loss is bounded. Okay. Now, the variance scaled to the diameter of the model space will actually determine the learning rate of the scaling of the effect for the multitask case. So now you see that we can maybe look at the scale. So if the variance is smaller than 1, then that thing is always smaller than square root of n. And remember, square root of n is what is the kind of regret you suffer, is the price of no communication. So if the variance is smaller than the scaled variance is smaller than 1, scaled with respect to the diameter of the one space, then it's okay to communicate. It's bigger than 1. It's not okay. It's good. It's just let's be alone. Let's learn alone. And the way this is done is by it's the following: agents will run on GDE, and they will share gradients using scaling factor chosen as a function of the variance. One question is how these agents know the variance, the global variance of the task. They don't need to know it; they can learn it. This is sort of a meta parameter that can be learned by adding a further layer of learning in each agent, and that works. And this game here is optimal up to constant factors. So there is in this setting, there is no better you can do. And these things can be implemented. So the algorithm, so this is the regret on the Y scale, and this is the number of rounds in the X scale. And the blue line is this hedge multitask of GD. And the red line is the learning independently. And the green line is like learning all the tasks at a single task. Okay, so these things are actually implementable. These are real world data. It's a length data set that is one of these data sets that are commonly used for multitask learning. So things to work here is nice, but we are limited to what we. So what happens if we are in a real communication graph? So now, if we are in a real, if we are on an arbitrary graph, so no, we cannot talk. It's not that each agent can talk to all the agents. We can actually use a reduction. We can reduce. We can locally reduce the problem solved by every agent to the key. So essentially, we can assume, we can virtually run each agent as if it were in a good program its neighbors. And this is done by, is a bit of overhead, so each agent will maintain a local model for each neighbor. Okay, and now the prediction of an active agent is computed by combining these local models that are stored by the neighbors. Okay, so now you see what happens. So now VT is active, so XT of VT is a prediction. So what the guy does, he will pull the predictions from the neighbors. So N of VT are the neighbors of the active agents. So he is pulling the model of the active agent VT that each neighbor U is keeping. So basically, the active agent is asking each neighbor, dear neighbor, can you give me the model of myself that you are storing so that I can use it to make it better. Okay, so this is a kind of a weird way of acting, and these W's are multipliers, the scaling the terms that will be appear in the regret. So now, after we do that, we observe the loss of the gradient, and then all the agents in the neighborhood will update the local models using the linear losses that will be built by combining the gradient of the loss, of the observed loss by the active agent, and these weights. This looks like a little, it's kind of a strange way, but of combining things. But the reason why we do this is because we would like to use the previous bound in this more general context. So how do we do that? So now let's look at the number of time steps where the neighborhood of a certain agent is active. Okay, so T of B is all the time step where some neighbor of B, including B itself, was active. And now sigma squared of B is the local variance of all the best model for the agents in the neighborhood of B. So that's local variance is important. And now the key observation is by doing that weird combination step with those local models stored by the agents in the neighborhood, we can see, we can apply the previous bound. The previous bound is the bound over here. We can apply this previous bound and now instantiate it in this specific setting. So now the previous bound was in the clique. What is the degree of a node in the clique? It's just the number of nodes in the clique minus 1. So we replace that parameter with the degree of V. And now we replace the variance, the global variance with the local variance for the node V. And then we replace the horizon T with the horizon cardinality of TB, which is all the steps where the node in the neighborhood was active. Okay? And it turns out that the multitask regret will be the sum of all these contributions for every agent B scaled by these weights. Okay, so that's the way this reduction works. We don't know whether this is optimal, but this shows an interplay between the local variances, the sigma squared B, the degree of the nodes, and that term, the cardinality of B sub B, which encodes also the structure of the graph. So this doesn't look very much interpretable. I cannot interpret it. So okay, let's make it. Let's assume that again, this bound holds for arbitrary activations, but now I can assume that nodes are stochastically activated with known probabilities. And I need to know the probability in this case, but this probability can be easily estimated. So now the kind of bound that you look at is simpler, although it's kind of weaker. So we are now looking at the max degree of the communication graph, and we're looking at the maximum over the local variances. But this is now the kind of scaling that you get, and you will recover the alpha parameter that you saw in the single task problem. Okay, so this is just the single task problem, but now it's a multitask. So we are doing worse than single task. If we were single task, we would do square root of alpha t. Because with multitask, we get again, we get some multiplier, which is bigger than 1. And this multiplier depends on this interaction between, the variance, the local variances, the worst case local variance, and the worst case degree of the graph. Okay. And again, okay, so these things can be implemented and can be run. In this case, it's a synthetic data set. And again, we are comparing this empty CO2 OL, which is the purple curve, the regret, against the independent learning case and the single task learning case. So, of course, again, here, there's no single question, right? Because there could be some tasks can be very different, some tasks can be very close. What is important that the close tasks correspond to neighboring agents. Whereas if agents are far away on the graph, their tasks can be kind of different. Because we are actually measuring the hardness using this notion of local variance. Okay, so any questions on the bound? Yes, yes.
With that, if you were to factor in communication, the law, then that should.
So the question is, if I factored the communication cost, communication complexity, the losses, will that change something? The communication complexity here is, okay, it's limited to the first neighborhood. So I'm doing this two-round communication, pulling the models of my neighbors, combining them, and then sharing the gradients. Well, it's a kind of it's a constant cost, which depends on the mass degree, of course. The network, that can be factored in, but that doesn't change the qualitatively in the kind of bound, because there will be a mass degree term appearing if you want to pay something for that. Okay, so yeah, what is important, there's no broadcasting. So I'm not So you can imagine a different messaging model in which I ask you, here, Negar, can you please relay this message to the guy there? That would really increase the message complexity in a way that scale exponentially with the degree, because you're multiplying messages as you broadcast them. However, here communication is limited, and everything is local. So communication is local, which is a very nice feature. A very appealing thing to this model. They are distributed, decentralized, and local. There was another question on the yes.
Yeah, I see TB was the time each agent was active before. You said
No, it's the entire neighborhood. It's a bit more.
okay, and this was reflecting this size of the network.
Yeah, because this is counting the time steps when any neighbor of some agent D is active, including D itself, because I'm counting D in the neighborhood. So clearly, if the graph is dense, these neighborhoods are large, therefore these TB terms are big. Okay. And yeah, so now that the thing, so you pay them that when you sum up over B, you pay the sum of those per terms. Now you're asking yourself, how can I make sense of these terms? Yeah, I can sort of make stochastic assumption and then massage those bounds, making them a little bit worse because I'm taking max degree and max, but then the alpha thing pops up there. So what is alpha? Is the independence number, and the dependence number is bounded by the size of the graph, and minus, the size of the graph is always not larger than the size of the graph, and it's larger when the graph is dense, which is exactly what we saw before. In those neighborhoods, those TB will be large when the graph is dense, and this is reflected by the alpha, which is large when the graph is dense. So yes, indeed, thanks. That is giving us some meaning to those terms over there.
Thank you.
Any more questions here? Yes. Okay, I need the mic for that one. Because I won't be able to. Also people.
So, did I understand correctly that this is you achieve along with an unknown distribution over the activation of the nodes?
But here I need to know, in order to be found, I need to know the distribution, the rate of activation for tuning the W's, for tuning these coefficients when I do the combination of the solution. And these things can be estimated, right? Because I can, so I don't need to know, yeah, this is the reasonable question, because I don't need to know the activation nodes of some guy far out in the graph. I just need to know the activation probability of the nodes in my neighborhood, which I can measure. So I can build estimates of these things, and these estimates will converge pretty quickly because these activations are independent of anything else, and therefore, essentially, I pay a small cost for not knowing the probability of activation in my neighbors. Yeah. So that is we have in the paper we do have a section on this. Okay, let me conclude with this online distributed organization. This is stuff I didn't do, but it's really cool. I like it because it's a sort of it's in the same ballpark, but it's actually a completely different angle to these problems. So this is the online version of distributed organization. What is distributed organization? Learning, and you have a bunch of agents. Each agent has a data set, and they want to build a common model, a common, let's say, they want to minimize empirical risk over the combination of all the data sets, of all the local data sets. But they don't want to exchange the data, they will exchange some model information. So you have federated averaging, so you have all these beautiful algorithms that do this job. And if we play out that this is a non-linear setting, it becomes online distributed optimization. And here, the idea here is that all agents will be simultaneously active because this problem is inherently different from the other things we saw before, although it's about motivated learning. So the idea here is that each agent has a local loss. The loss is actually local to the agent. You see, LT is has two arguments, is V because the loss of agent V, and then X because it depends on what the agent V will predict. Okay, so that's the loss of LT of agent V choosing X. And then there's a target loss. The target loss is the thing against which all agents are going to be measured. And this is the average of all losses of the agents, of all the local losses of the agents. So the good thing here is the following, is that the agents have partial knowledge of their task. What do I mean? So I mean that things go the following. All the agents are active. So every time that every agent wakes up, we will compute the predictions by combining the agent's models before. So the protocol is the same. And the agent will incur, each agent will incur the target loss. The target loss over the local decision of the agent. So I make a decision and I pay the target loss, but I observe the gradient of the local loss. So I have partial knowledge of my task. This is what I mean. Oh, wow. So, and then I can share the local loss gradient with the agent. Okay. So now the problem here you see is that I would like to that everybody tells me their losses because I need to combine these losses. I can combine the gradients, which is the same thing, but I need to get them. And however, I can only talk to my neighbors. So what is crucial here is the time it takes for information to diffuse over the graph. So it's a diffusion problem, really. And so let's look at the regret. The regret looks very much like the single class case. But so we are still every agent is being scored against the best global model. However, the agents are scored using the target loss, and we are looking at the max. So all agents are simultaneously active, and now we're looking at worst case loss over the agents. Worst case cumulative loss over the agents. I want to say, okay, every agent is desperately trying to learn this target loss just by observing local information. And now I'm looking at the guy who's performing the worst with respect to the best global model. Kind of things. So the communication model and the two-round algorithmic framework is exactly the same as in multitask, but the objective is inherently different. And what it turns out here is that by ignoring communication, agents here in this distributed optimization setting pay a very high price. Because if they don't talk to each other, they will never know what is the target loss. So they will incur linear regret. Whereas in the single task case, if I don't talk to my neighbors, I will pay a screw event price. Because I will do that simple genesis input now. So you see that here agent will have to use communication at all costs, otherwise there's no learning at all. And so there's some cool, there's actually a paper called this year that achieves the optimal regret in this problem. And this regret depends on the square root of t, the number n of agents, and this term at the denominator, which is 1 minus the spectral ratio of the communication graph, which is the ratio between the smallest non-zero eigenvalue and the largest eigenvalue of the Laplacian of the communication graph. And yeah, so then it's a notion of spectral graph, the same. So this is the cost of diffusing the gradient information across the graph. And yeah, oops. So this is I'm almost done. This is so the idea here is pretty much different. I need all the agents to be active because this is the way I define the regret, and this is actually the only way. So if one agent is active at a time, this problem becomes impossible. Because there's no way you can learn what was the loss of the time step for the other agents. So I cannot reconstruct the target loss locally. And the only way to reconstruct the target loss locally is by infusing information and then receiving information from that. And that's the cost. Okay, so there's a bit of a wrap up here. So we saw single agent, single task. We saw multi-agent single task on any graph, which scales with the square root of the independence number of the graph. We saw the multi-agent multitask on a click, which scales with the mass degree, which is n-1 of the click, and the global variance, the click variance of the decimal of tasks. Now we saw the multi-agent multitask on any graph in which we replace the variance of the task in the click by the local variance, and then the alpha will go up in the stochastic activation phase. And then we saw this distributed optimization on any communication graph in which things scale rather than with the independence number, we scale with the spectral gap of the graph. Because the problem now is really on the opposite side of the spectrum, because I need to force communication at all costs. I don't have the option of withdrawing from communication as I had it in the multitask case. Okay, some two open problems or some open problems. Yeah, we don't know whether this multi-agent multitask bounds with the local variances are optimal. They're kind of not very interpretable in general. We need to make some assumptions to make them interpretable. So we need to have something nicer or maybe optimal. You can consider online distributed optimization with random participation. So now assume that actually maybe a random subset of the nodes will participate in the gossiping algorithm. That makes the problem harder because the diffusion on a random subgraph is harder than the diffusion on the entire graph. So we're going to have some random spectral graph over the induced graph by the agents, by the subsequent participating agents. So this can be done and it can be analyzed. And the other problem, which is kind of cool, I tried to solve it, but I really didn't manage, is okay, if you do online distributed optimization with dynamic feedback, this can be done, and the bound will look very much like the previous one, but the dependence on the horizon will be t to the 2/3 instead of community. And if you do bindings, you immediately feel the pang when you see t to the 2/3 and you don't have a much lower bounds because you typically push through this square root of t. And there's no lower bound above the square root of t, and there's no way. I mean, the analysis for getting t to the 2/3 is quite elementary. It's almost immediate from the full information analysis, and I have no idea how to improve on this. Thank you very much for your attention. Thanks. Maybe some more questions.
We're going to have now a question. The audience are going to ask questions. Have online audience.
Yes, so thank you very much for the great talk. I have a very general question. So this notion of inactive agents that seems to be quite central to the results. And I'm lacking a bit of a practical intuition where this might occur in application.
Yeah. So one of the things, first of all, think of a non-asynchronous model. So if all agents are active at the same time step, it means they're synchronized. So there's a synchronized involved. If agents are active in a synchronous way, their activation sequence will be distributed along the timeline. So at every point of time, there's going to be some active agents. In general, which we did it in the paper, you can assume that every agent has a certain probability of becoming active, and then you flip the coin for each agent. This can be done, and this is a more general setting. Right.
So yeah, say something to do with the network bandwidth or something.
No, this is more okay. Again, you can do it as sort of a modeling asynchronous working, and it's a desynchronized, there's no global clock. So agent will do things in an order which is in a way that is not synchronized. Or you can think of in federated learning. In federated learning, agents can participate or not participate in to the data exchange, to the round of federated learning, whatever. So this is something that is done because maybe there's a mobile client which is online and it's not providing data. So this is studied in federated learning. Yeah.
One more question from audience here and then one.
Thank you. I was just wondering what changes if you're allowed to choose which of your neighbors you can trust.
Yeah. This is very, very, very interesting question. Absolutely. Yeah. Yes, we try that. We try to do so because, of course, I mean, maybe your local variance is kind of small, except for one guy, which is really not, or even more. Maybe there's some bad agent, literally, that is trying to, to do something and is doing random, sending out random grades and stuff. So we got to cut this guy off. And so the idea is now we are now in an online deterministic meaning adversarial setting. So you never know whether this is a really bad agent or the person is trying to make you believe that this is a bad guy, but is actually in the long run is not to be a good guy. So we try because this is absolutely a legitimate question. Because especially in federated learning, there are these bad agents, so there are maybe agents that either go awry, they start spitting out random stuff. So this is a real problem, and so this is something that we would like to address. And we don't have an elegant solution, so I didn't show it. There are some solutions, but yes, we should. It's a good question.
Any one more we can take from the audience, or we can do the copy break.
If you look at that way,
Thank you very much. Thank you.